Presentation number 2, Teresa Slivnik. Part 1. This is the general equation for the linear congruence and how to solve them. Throughout the presentation, I will be filling in for A, B, C, and M. 2x plus 3 is congruent to 4 in mod 5. First, you subtract by 3 on each side to get x alone. So you would end up with 2x is congruent to 1, and you would have to divide both sides by 2 to get x alone, but on the right side you would end up with a half, and that's not a whole number, and so you would have to find, on the next slide we'll see a number congruent to 1 that is divisible by 2. So when you construct your table in mod 5, you can see the numbers that are divisible by 2 that are congruent to 1. So 6 would work, 16, 26, and 36. So you can plug in 6 for 1 in the equation because 6 is congruent to 1. I chose 6 because, like I said, it's congruent to 1, and it's a multiple of 2, and it's a small number. Now you divide by 2 on each side to get x alone. 6 divided by 2 equals 3, which makes our solution x equal 3 in mod 5. Now that we have found x in mod 5 one way, we're going to look at how to solve for it in another way. We are using the same linear congruence equation as before, and so, like previously, the first thing we do is subtract 3. In the first equation you had done, you had to find something congruent to 1, the one in red. However, in this case, you need to find a number congruent to x that when multiplied by 2 will be congruent to 1. So you're trying to find a number that you can multiply 2 by that will be congruent to 1 in the blue. We chose 3 because 2 times 3 is equal to 6, and you can see here that 6 is congruent to 1. Here we are multiplying both sides by 3. So now you get 6x is congruent to 3 in mod 5. And because 6 is congruent to 1, you can simplify 6x to just 1x, and your solution is x equals 3 in mod 5. Now let's look at a problem that won't run as smoothly. 6x plus 1 is congruent to 4 in mod 8. In an attempt to get x alone, you must first subtract by 1. The result of this is 6x is congruent to 3 in mod 8, and so now we will look at our mod chart to see if we can find any congruencies. When looking at the mod chart, you can see that there are no numbers that are divisible by 6 and congruent to 3 in the chart. There are also no numbers that we can multiply by 6 to get a congruency of x. Because of the pattern 1, 9, 7, 5, 3, 1, 9, 7, 5, 3, and so on and so forth, it is clear that there will never be a possible solution. Part 2. In this section, we will be looking at divisibility rules into other bases. So we're specifically looking at base 4. And in base 4, a number is divisible by 4 if it ends in 0. This is our claim. Let n equal d2, d1, d0 written in base 4. N is divisible by 4 if and only if d0 equals 0. To prove this, we expanded the notation, and so we did d2 times 4 to the second plus d1 times 4 to the first plus d0 times 4 to the 0. And this would actually be d2 times 16 plus d1 times 4 plus d0 times 1. As we continue to prove it, on the congruency chart, 16 and 4 are both congruent to 0, so we can replace these two by zeros. This leaves us with the ones place, which is the only place value that is relevant when dividing by 4. Our claim is that in base 4, a number is divisible by 3 if and only if d2 plus d1 plus d0 is divisible by 3. Much like proving the other one, to prove this one, we are expanding the notation. So d2 multiplied by 16 plus d1 multiplied by 4 plus d0 multiplied by 1. And you can see that 16 and 4 are both congruent to 1, and so you can end up replacing these with 1. Because of this equation right here, we were able to break it into two different parts, this one and this one. We found that this one works because 15 and 3 are divisible by 3, and we have 1 extra left over from the 16 and the 4 and the 1, and so that's how we get this equation, which proves our claim. And that concludes this two-part presentation. Peace!